So in this video, I need to introduce you to a concept called related rates. Um, Up to this point, we've really only dealt with one rate so far, one derivative, and that's been dy dx. Dy dx we know represents the rate of change of y with respect to x. And sort of what that means is how fast is y changing compared to how fast x changes. And so effectively, I mean, this is slope, right? That's what dy dx is. But every problem has only had one derivative in it. It's only had one rate in it, and that's been dy dx. And what's going to happen in the coming problems is we're actually going to have multiple rates. And in particular, a lot of times they're going to be with respect to t. And what that means is we're going to be talking about speed. So the first one that I have here is dx dt. So dx dt is basically just the rate of change of x with respect to t. And practically what that means is it's how fast is x changing over time. So dx dt represents how quickly x is changing in a problem. Similarly, dy dt means the rate of change of y with respect to t. In other words, how fast is y changing over time? And we could have any variable up here. We could have dr dt, that would be how fast is r changing, or dv dt, how fast is v changing. But when it's with respect to time, it's all about how fast something is happening. When it was dy dx, it was how fast is y changing compared to x, and that was slope. But in these problems, it's about time. Okay, so I'd like to look at sort of an example of this graphically, and I think it gives us a chance to see some neat stuff. So in a little bit here, I'm going to show you an animation on the left side of the screen. So in the animation to the left, you're going to see this point I, and it's actually going to move along the curve, right? So this point down here, I, is going to move along the curve. As it moves, the point E is going to sort of shadow it. Like E basically represents the x coordinate of I, and you're also going to see that M sort of shadows the point. M is the y coordinate of I. And what I want you to look for, and I'll play the animation a couple times, I want you to look and see, what do you notice about the motion of E, and what do you notice about the motion of M? So just watch E, watch M, and sort of pay attention to how they move, right? So here we go. I could have given some commentary there, but sort of decided not to. What I hope you notice is that as this is going along, E is moving at sort of a constant speed across this thing. Whereas M, like, is going faster right here, and then it sort of slows down and actually stops, and then sort of speeds up again. In fact, if we watch it again, watch how fast M goes in the beginning. Right? When I first time, like, M is like rocketing upward. What that should mean is M is sort of telling us that in the beginning, dy dt was very fast, very positive. Um, in fact, when we were in this middle section, when M is going downward, that means y is changing negatively. That would mean that dy dt is negative. Whereas the whole time, E, or rather dx dt, this is just saying, hey, look, everybody, dx dt is a small positive number. Here we are. At this point, M coming down means dy dt is negative. Heck, right there, it means dy dt was 0, because M wasn't moving up and down at all, right? So when we talk about dx dt and dy dt, we sort of mean, what can we say about how quickly the x and y coordinates are moving? So I want to look at this computationally. So we're going to look at two examples really quickly. So this function over here is this function, y equals x cubed minus 2x squared plus 1. And I'm just going to tell you right now that this is the relationship of the rates. I'm not going to tell you where it comes from. We'll talk about that in the next video. But trust me for a minute. Dy dt, the speed of y changing, is equal to 3x squared times dx dt minus 4x times dx dt. And I might ask the question, find dy dt. In other words, find out how fast y is changing when, because remember, the speed of y changing was variable, it changed. Find the speed at which y changes when x equals negative 1 if dx dt equals 1. Well, we should be able to take this equation, and we should just be able to evaluate it. We should be able to just use these values. We'll get that dy dt is 3 times negative 1 squared times dx dt, which is 1, minus 4 times x, which is negative 1, times dx dt, which is 1. If I solve this thing, I'll get dy dt equals 3 plus 4 which is 7. And so what should that mean? That should mean that when we are at x equals negative 1, so this is where x equals negative 1, when we are at this point right here, we should be noticing that dy dt is 7 compared to dx dt being 1. In other words, y is increasing 7 times faster than x is. Now, if we watch this thing one more time, do we believe that? When we are right here on the graph, when I gets there, do you believe that m is going up 7 times faster than e is going sideways? Let's take a look. I completely believe that. Like, m is moving up very quickly, e is moving very slowly side to side. And that's sort of the point that I want us to see there. Well, sorry about that. Isley decided she really wanted to show up in the recording, and not much I can do about that. So let's go on and look at the next example that I have. So sort of very, very similar question, right? If this is indeed the relationship between the rates, can we find out what dy dt is? Can I find out how fast y is changing now when x is positive 1 if dx dt is sort of a constant speed of 1? So we could do the exact same thing. We could say that dy dt is 3 times 1 squared times 1 minus 4 times 1 times 1. And if we solve this, we'll end up finding that dy dt is 3 minus 4, which is negative 1. And again, we can check the graph for this. We can check and see when x equals negative 1, I'm sorry, when x is positive 1, that's right here. So when I get to that point right there, if dx dt is 1, dy dt is supposed to be negative 1. So we should notice is that when we get to this point, e should be moving sideways to the right in the positive direction, exactly the same speed as m is moving downward because it's supposed to be negative 1. And so we're gonna take a look at that really quickly, right? So here it's moving up, m's moving really, really, really fast, slows down, stops, and what we're looking for is right here at this point coming up. At that point, I think it's clear, and I mean the equation shows it. E is moving positive at a speed of 1, m is moving negative or downward at a speed of 1. They're moving at the same speed, it's just that one of them is a positive movement and the other is a negative movement. So that's the concept of related rates, that if one quantity in a problem is changing, the other quantities are changing, and we can look at the rate at which those quantities are changing.